Hi, this is the second video of my playlist about the preparation of phenethylamines. In this video we'll have a look at the preparation of phenethylamines by aminoethylation of arenes and Aryl Halides. A number of powerful strategies have been developed to accomplish this reaction, and I'll show you specific examples in a minute. One strategy is electrophilic aminoethylation. Electron-rich arenes can be aminoethylated electrophilically, for example by treatment with aziridines, haloethylamines or nitroalkenes, usually in the presence of acidic catalysts. If a given arene is not reactive enough or reacts at the wrong position, an aryl halide can be converted into a more nucleophilic organometallic reagent and then treated with a suitable electrophile. A second strategy is aromatic nucleophilic substitution with a nucleophilic aminoethyl derivative or with a metallated nitrile or amide, followed by reduction. Alpha-amylation of ketones and reductive amination is another convenient route to phenethylamines. I'll show you now specific examples of these strategies. Here, Friedel-Crafts acylation of benzene with protected alanine gave a fair yield of the expected ketone. Trifluoroacetyl and phthalate protective groups are particularly well suited for these strongly acidic conditions. The temperature and the amount of pyridine must be kept as low as possible because ketones and acyl chlorides easily racemize. In this instance, the protected aminoketone was deoxygenated by hydrogenation in trifluoroacetic acid. Toluene is more reactive than benzene and could be acylated in high yield with the acyl chloride of F-MOG-valine. Friedel-Crafts acylation of toluene proceeds with high regioselectivity, as in this example. Alternatively, aminoketones can be prepared from amino acids under alkaline conditions by acylating Grignard reagents with Weinreb amides. In this instance, the ketone was racemic but could be converted into an enantiomerically pure amino alcohol by ruthenium-catalyzed hydrogenation and simultaneous dynamic kinetic resolution, without hydrogenation of the alkyne. Dibromoenamines, like the starting material of this example, can be prepared by treating formamides with carbon tetrabromide and a phosphine. These enamines have the same oxidation state as glycine and react like an activated glycine derivative. Here, Suzuki coupling with a boronic acid followed by hydrolysis yielded a protected aminoketone. Enamines are nucleophilic at position 2 and electrophilic at position 1. In the presence of acids, arylation with electron-rich arenes should therefore yield benzylic amines, not phenethylamines. As shown here, however, some catalysts can promote arylations at position 2. As discussed in part 1 of this video playlist, nitroalkenes are easy to prepare by aldol condensation of nitroalkenes. These electron-deficient olefins are good Michael acceptors and can be used to alkylate electron-rich arenes. In this example, indole was alkylated enantioselectively by a nitroalkene and 1% of a chiral nickel complex. Here, an electron-rich phenol was alkylated enantioselectively by nitrostyrene with the aid of an enantiomerically pure thiourea. Also, some polar organometallics can add to the CC double bond of nitroalkenes, as in this example. The less selective Grignard or organolithium reagents, however, can also form a carbon-nitrogen bond with the nitro group, or even displace the nitro group entirely. Like iminium salts, also acetals can be used as electrophiles for Friedel-Crafts type arene alkylations. If such alkylations are conducted in the presence of acid-resistant reducing agents, for instance acylane, the initially formed benzylic ether might be reduced to an alkane, as in this example. If less acid or silane was added, however, a twofold arylation of the acetal occurred. Intramolecular reactions proceed much faster than intermolecular reactions if 3, 5 or 6-membered rings are formed. In this example, an acipene was prepared by intramolecular reductive alkylation with an acetal. Alpha-amino or alpha-hydroxyacetals, like the starting materials of the previous two examples, are more resistant to acid-mediated carbocation formation and hydrolysis than simple unsubstituted acetals. Nitrogen and oxygen are more electronegative than carbon and destabilize carbocations by induction through sigma bonds. Once formed, however, these carbocations are more electrophilic than those generated from simple acetals. Similarly, glycosides are more resistant to hydrolysis than would be expected, again because of the electron withdrawing effect through sigma bonds of the alpha-hydroxy group. Even more difficult is the conversion of unprotected alpha-amino acetaldehyde acetals into carbocations, because of electrostatic repulsion by the ammonium cation. In the previous example, the cyclization only worked well after acylation of the amino group. For this same reason, aminoethanol cannot be used for the direct acid-catalyzed aminoethylation of arenes. Aminoethanol can, however, be used for aminoethylations if first converted into an oxazolidinone, for instance by sulfonylation with sulfuric acid followed by treatment with carbonate. Friedel-Crafts alkylation of benzene yielded a mixture of phenethylamine and diphenylethane. Aziridines are generally more reactive than oxazolidinones, and many examples of electrophilic aminoethylations with aziridines have been reported. Here, a lithiated arene was first converted into trifluoroborate and then alkylated with a Boc-protected aziridine. Nucleophilic attack occurred at the less substituted carbon atom. In this example, a cuprate was alkylated by an N-sulfonyl aziridine. Unlike in the previous example, the reaction required heating for 18 hours. This here is an example of a dynamic kinetic resolution during a nickel-catalyzed aminoethylation with an aziridine. The arylation occurred at the benzylic carbon atom and not at the less substituted methylene group. At some stage, insertion of nickel or manganese into the benzylic carbon-nitrogen bond probably occurred. Also in this example, arylation took place at the benzylic carbon of the aziridine. Other than carbon nucleophiles can also attack the benzylic carbon atom of aryl aziridines, even of aziridines devoid of acyl or sulfonyl groups. Here, the nucleophile was N-methylaniline, and with just 5% of copper triflate and at room temperature, a clean alkylation at nitrogen occurred. As an alternative to electrophilic aminoethylations, nucleophilic aminoethylations can for instance be achieved by arylating a metallated nitrile. Reduction would then yield phenethylamines. In this example, acetonitrile was phenylated with chlorobenzene and potassium amide in liquid ammonia. A mixture of two arylated acetonitriles was obtained in low yield. 2-chloropyridine undergoes aromatic nucleophilic substitution more readily than chlorobenzene. In this example, butyronitril was arylated by 2-chloropyridine with the aid of an excess of a strong base. Despite the excess of reagents, no twofold arylation occurred. Here, an excess of nitrile was used to alkylate a dichloronicotinate. The arylated nitrile was then reduced to the amine with sodium borohydride and cobalt chloride. You can find further examples of nitrile reductions in the first video of this playlist. As mentioned there, benzylic nitriles are difficult to reduce to amines because of the easy reductive decyanation by C-C bond cleavage. This might have been one reason for the low yield of lactam obtained here. Malononitrile is a strong acid and deprotonated malononitrile therefore a weak nucleophile only. Under the optimized conditions shown here, however, it was possible to arylate malononitrile with an aryl iodide. A large excess of malononitrile was required, though. Oxidation in the presence of an excess of nitromethane yielded an alpha-nitroacetophenone. You can find examples of the reduction of such nitroketones in part 3 of this playlist. One convenient approach to substituted phenethylamines is alpha-arylation of a ketone followed by reductive amination. Palladium catalysts are available today which enable high-yielding ketone arylations with aryl bromides or even aryl chlorides. In this example, propionone was arylated in high yield with an aryl bromide. Reductive amination with ammonia and sodium borohydride then gave the target phenethylamine. One odd reaction is the metallation and arylation of ethyl carbamates at the methyl group. Under optimized conditions, the main product can indeed be a protected phenethylamine and not the expected benzylamine. A more straightforward method to generate metallated ethylamines is by halogen-metal exchange. The yield here wasn't high, perhaps because of protonation of the organozinc intermediate by the carbamate. One further alternative is the use of aminoethylboranes as nucleophiles. These are more resistant to protonolysis than polar organometallics and undergo high-yielding Suzuki-type coupling reactions with aryl bromides, as in this example. The trifluoroborate was prepared by hydroboration of a vinyl carbamate followed by treatment with fluoride. These compounds are often solids and can be isolated and stored. The addition of carbon-centered radicals to allylamines can yield aminoethyl radicals, which may then add to arenes. In this example, a benzoyl radical was generated by hydrogen abstraction from benzaldehyde. The target product was formed in high yield. Aminoethyl radicals can also be generated by adding a nitrogen-centered radical to an olefin. This strategy was used here to prepare a substituted benzazepine. Nitrogen-centered radicals can also be generated by oxidation of nitrite, as in this example. Addition of this radical to a metacrylamide and then intramolecularly to an arene yielded a nitroethyl arene. Another weird way to prepare phenethylamines is by rhodium-catalyzed coupling of acrylates with aryl boronic acids in the presence of an electrophilic aminating reagent, a dioxazolone in this case. Such reactions can also be catalyzed by a mixture of cobalt and silver, as in this example. This is perhaps mechanistically interesting, but the final product can be prepared easier by condensation of an acylactone with salicylaldehyde and hydrogenation, as discussed in the first video of this playlist. One way to prepare alpha-oxophenylacetamides is by twofold carbonylation of an aryl halide in the presence of amines. These ketoamides are often obtained as byproducts in palladium-catalyzed carbonylations, but can become the main product under optimized conditions. Here, the ketoamide was reduced to an amino alcohol by treatment with borane. Instead of iodine, other acids, such as sulfuric or trifluoroacetic acid, can also be used to generate borane from borohydride. Most potential side reactions are discussed in the first video of this playlist. During Michael additions to nitroalkenes, the nucleophile may also form a carbon-nitrogen bond with the nitro group, or may displace the nitro group completely, as in this example. Hard, polar organometallics like organolithium and organomagnesium reagents tend to react with the nitro group, while softer organometallics like organopalladium compounds or cuprates will preferentially add to the C-C double bond. Here are some further references which you can also find in the description of this video. Under the Community tab of my channel, there's a PDF version of the slides. The next video of this playlist is about the preparation of phenethylamines by CN bond formation, for instance the alkylation of amines with phenetyl halides or epoxides. So long.